Okay, so thank you for the introduction, and I would like to thank the organizer to let me the opportunity to present my work today. So I'm Maxime Tannious, a third-year PhD student working in Grenoble with Roman Legal and Alexandre Faure. And today I will talk about my work on the anatomy of the class 1 protostar L1489 IRS with NOEMA. Okay, so I will start with a bit of context and present you the targeted source, and then present to you some results that were published earlier this year on this paper in ANA. And then I will go to some work in progress to derive the mass of streamers that I will show you in a moment, and then finish with some project. So I remind you here just a quick, the star formation process of Loma stars that is starting with the collapse of a prestellar core. And due to the conservation of angular momentum, a disk is formed around the newborn star. And this is embedded in gas envelopes, which fade away with time. And this disk may eventually form a planetary system. And we know that there is a rich chemistry in the star-forming region, both in gas and solid phase reactions happen. And there was some studies about the early phases, like the prestellar core in the class 0 phase, and the late stage, like the class 2 phases. But there was few studies of young class 1 stellar objects. And there is one question that is raised, is what is the interstellar legacy or the chemical reset at this class 1 stage? So the target we choose is L1489 IRS. It's a perfect target. So as you can see here, it is shown at the tip of the red arrow. And it's an ideal target to study interstellar heritage because it's embedded in this parental molecular cloud. So we can study the different scales from the parental molecular cloud to the disk. And so this source was studied with many previous interferometric observation, as you can see here. And what we can see on this list is that many studies focus on the carbon monoxide or its isotopologue lines, or some other on a 1 millimeter line, but there was few observation at 3 millimeters, and the latest one are pretty old, like 2001. And having a 3 millimeter observation is crucial to derive correctly abundances for subthermally excited species. And so that's what we did. We conducted NOEMA and IRAM 30-meter observation, focusing on the 3 millimeter band to do a molecular survey at high spectral resolution and high angular resolution. And that's what we saw. So we saw a large diversity of structures, and before doing chemistry, we wanted to identify what was going on and which molecule traces what, which structures. And so that was the aim of the work, to identify these different structures. So we can see some dense envelope that is traced with some lines. We can see some outflows, also inflows, streamer, and with this, the disk also in fainter species. And so I will focus mainly my presentation on the detection of the streamer that we can clearly see in the HC3N line. So there was a previous observation in polarized intensity in the infrared led by Lucas and collaborators in 2000 that showed that the structures around the protostar was structured around two major axes, the primary and the secondary here. And they interpret this as bow shocks that would be linked to outflows emission. And we have on the right-hand side here our observation. So in the background, we have the HC3N emission, and on contours, the blue shifted CS emission. And we can see that we retrieve these structures elongated along these two major axes, the primary and the secondary. But when we are looking at the literature, the HC3N generally traces inflows or streamers. And so we have two different explanations for the same structures. And so we need model to distinguish between the two. So that's what we did. We used the streamlined model that was implemented by Jaime Pineda and collaborators in 2020. And basically, this model is taking into as input the initial angular velocity of the cloud, the central object, the mass of the central object, excuse me, and the initial position of the gas particles that will fall onto the central object using freefall motion. And so you have the results here. So on the first column, the contours are the emissions that we see in our observation. In pink, you have the best fit trajectory that we find with the model. And in the second column, you have in the background an estimation of the velocity profile from the observation. And in pink, also the velocity profile estimated from the model. And so what we saw is that along the primary axis, we had trouble to find parameters that fit both the emission and the velocity profile, and therefore we concluded that it's unlikely to be a streamer. And actually, it may be a part of an outflow that is detected in a CO observation from Yen 2014. On the other side, looking at the secondary axis, we saw that multiple parameters fitted the observation, and so we concluded it's likely to be a streamer. And to confirm that, we ran another model that is a TIPSY model. So it's a recent Python package that is based on the same principle as the streamlined model, but instead of tuning by hand the parameters, it takes directly as an input the PPV cube and fits the observation. And so we find the same results, and you have here on the right-hand side a 3D plot of the trajectory of the streamer that is likely connects to the disk. And actually, it may be the origin of the external warp disk that is seen in this system. Is sufficient mass is imported by the streamer onto the disk, but I will come back to that later. And there's also a nearby prestellar core near the protostar, and it seems that these streamers emerge from this core and may connect to the disk. We also see a correlation between the length of the streamer that is here seen in the blue shifted emission, but also in the red shifted part, and the peak intensity of the SO line. And so we interpret this as shocks, accretion shocks of the streamers onto the disk. And what we can compute from the trajectories that we derived with the model is that if the aspect ratio of the disk is larger than 0.4, the streamers fall into the equatorial plane of the disk. And when we go down to 0.3 aspect ratio, the inclination is 3 degrees, so very near the equatorial plane. So that would support this accretion shocks hypothesis. So to come back to the streamer mass, so this is work in progress. So basically, we want the mass of the streamer, and we have a reserved map with NOEMA, as I've shown you just previously, but we got only one line. And we want to derive a Coulomb density map of H3N, and using one line, that means that we have to assume an excitation temperature. But we have on the other side few lines, 5 lines actually, with the IRM 30 meter, but the streamer is not resolved. But those 5 lines will enable us to derive an excitation temperatures. And using the intensities that we have with the NOEMA map, we can have a Coulomb density map of H3N. And assuming an abundance of H3N, we can have a Coulomb density map of H2 and having the mass after all. So that's what we did. Using the rotational diagram method on the H3N IRM 30 meter data. So there is assumption like the LT assumption, and this led us to having an excitation temperature of 7K. And using these excitation temperatures, we can derive the Coulomb density map of H3N along the streamer. But now we have to have a proper estimation of the abundance of HC3N, and we can see that it's actually a critical parameter to derive the streamer mass. So you have on the left-hand side here the streamer mass according to the HC3N to H2, and on the right-hand side the same plot but for the inflow rate. And you can see that depending on the abundance that we take, the mass and the inflow rate can vary for a few orders of magnitude. So it's a very critical parameter. And actually, the plot that I've shown you earlier is based on the literature's parameters. So the plot is varying from 10 to the minus 10 to 7.4 10 to the minus 9. That was observed in a few stellar objects. And using these parameters, you can derive a streamer mass and an inflow rate. And the parameter that I'm interested in here is to try to derive the amount of mass that will be due to the inflow. And you can see that depending on the HF abundance you take, you can go for more than 300% to 12%. So it varies a lot. And so we tried to do a first estimate of the abundance using a Radex model. So it's a very preliminary result that need to be tuned. But using this abundance that we derived from fitting the line intensities, we end up with an amount of mass that would be around 73%. So what you should retain here is that depending on the abundance, we can have a significant different result, but a significant part of the disk mass could come from the streamer, supporting the warp disk origin that I showed you earlier. So stay tuned to have the final results. It should come out soon. And so I will finish with some take-home messages. So you have here a simplified sketch of what's happening in this source. So it's a very complicated source. And we discovered a new at least 3,000 AU long streamers here in HC3N, but it is also detected in some other carbon species, which is likely connects the nearby core to the protostar through a gas bridge. And as I shown you here, it's also likely at the origin of the external warp disk. And there is a potential second outflow that may be the confirmation of the binarity of the system. And so to confirm this link between the core and the disk, we need a mosaic observation because the emission is going further than the NOEMA's primary being. And so it's ongoing observation. And now that we have distinguished the different structures, we can do a chemistry and excitation in the structure and compare what's happening in this different region. And on this, I thank you for your attention.